Okay, so to show that the Schrödinger equation follows from the path integral, let us remind ourselves the definition of the propagator. So the propagator tells us what the wave function will be at a future time if I give you the wave function over all of space at a past time. So that is what the propagator does. It is essentially the time evolution operator in the coordinate representation. Okay? So now let's take the time t to be infinitesimally separated from t prime. So it's just a little bit after t. So t is going to be t prime plus delta t, where delta t is very, very small. It's infinitesimally small. Okay? So then the above equation can be written as x, say t prime plus delta t is equal to the integral of dx prime. And here we are going to have x t prime plus delta t. And then we're going to have x prime t prime ket psi of x prime t prime. Okay, I'm just writing the same equation again, but for this for a small interval of time. Now, if it's small enough, according to Dirac and Feynman, we can write this thing. We can approximate it by a straight line segment, right? Part of some path. So we can write this as x. So, here x and x prime are fixed. And we are drawing, so we are drawing a straight line between them. Okay, so x, then we can write x t prime plus delta t to be x prime t prime. And we saw that that was going to be a prefactor m divided by 2 pi I h bar delta t is a square root for this whole prefactor. And then multiplying this times times an exponential of a discretized version of the action, so I by h bar, and delta t is the integral over time. And then we have the kinetic term, which is m v squared. But what is v squared? It's x minus x prime squared divided by delta t squared. And there is a half here because it's the kinetic term, so it's half mv squared minus v of x minus x prime by 2, and that is the so this is basically according to the Feynman and Dirac prescription. So okay, now what we can do is that we can just simplify this a little bit. Let me just copy and paste the prefactor because that's not going to change. And this thing, I'm going to simplify, but first let me paste it. And what I will do is I will, this delta t, if it goes in, then, a factor of delta t vanishes from here. And so let me make some room here. And there will be the factor of delta t will now be multiplying this. And we can write I here and h bar here and get rid of this bracket. Okay, so I'm just doing something trivial. Okay. So now let's define psi, which is a x prime minus x, the difference in the final and the initial and the final position. Now if I look at this as, say, as the x varies, what happens is that this thing fluctuates wildly, right? Because it's a small time interval, 1 over h is a small number. And so and here we have a phase. So as you change x or x prime, as you change the difference, this thing varies wildly, right? So in that integral that we were doing here, most of the contribution for this guy will only come from the narrow region in which x and x prime are almost same. In other words, the contribution to the integral will come from when psi is very small. Okay, we're around a small region, around psi equals to 0. Okay, contribution to the dx prime integral will mainly come from a small region around psi equals to 0. So this justifies, taking psi to be small and doing an expansion of these guys in terms of psi. Okay, that's the whole point of this. So if I do this, then the right-hand side of this equation just becomes, now instead of dx prime, the integral, I can change the variable and do the integral over psi. And then I have my prefactor, which I'm not going to change. It's m divided by 2 pi I h bar delta t to the power half. And the exponential, it'll just remain like it is, I psi squared m divided by h bar 2 delta t. But then what I do is that I then expand the exponential containing this thing, okay? Because this thing, we are taking delta t to be very small. So we first expand in delta t. So if I expand in delta t, it's going to be 1 minus I delta t divided by h bar v of psi by 2. And then what we will do is that this thing is actually multiplying, so we are expanding this equation now, okay? So this will be multiplying this guy, right? So that guy we can also expand. And if I expand this, that thing will be psi of x and t prime plus psi d psi x t prime by d of x, then psi squared del squared psi x of t prime del x squared and higher order terms. Okay, so there are all these terms. And then what we can do is that we can expand this thing as well, because psi is very small. So psi v of x minus x prime by 2 is v of x minus psi by 2 del v by del x, right? And dot, dot, dot. So now we can put all of this together and see that there is an integral sign, and there is a Gaussian and multiplying various factors of psi here. So, we can do some Gaussian integrals. So let me remind you what the Gaussian integrals are. I think by now you should know them quite well. So d of psi exponential, when I don't write, of course, the limits, they're the usual, exponential of I psi squared. So this is a complex Gaussian integral, and which is a different, its derivation is actually different from the real one. If you don't know how to do that, let me know. I can show it to you some other time. It's actually a contour integral. So this thing is going to be 2 pi I h bar delta t by m. By now, this is something that is probably very familiar to you. But the second one that we need is we need the higher moments of this integral. What about the first moment? If I have, say, psi, because there is a term like that, right? When this factor multiplies 1 and this thing, right? This doesn't depend on psi, but there's a linear factor in psi. So what is the integral for this? Do you know? Okay, let me ask you another question.
0?
0, exactly. Why?
Odd function.
Right. The integrand is an odd function, and the limits of the integration are symmetric around 0, right? So, for example, what is this guy going to look like? It's going to be a Gaussian multiplied by a linear term, right? So this thing will look something like this. Like over here, it'll look like a straight line, but as you go away, it'll look like a Gaussian. And because it's an odd function, the area under the curve here will be equal in magnitude, but opposite in sign to the area of the curve under here. And therefore, they will cancel out. Okay? So this is 0. And then what we can do is that we can take the derivative of this guy with respect to delta t. If I take the derivative with respect to delta t, it brings down psi squared. And so using this equation, but taking the derivative with respect to delta t, we can derive very easily the integral where the second moment of the Gaussian distribution. Okay? And if you do this, it's square root of 2 pi, and then times I h bar delta t by m. I never have these things memorized. I always have to either look them up or have to redo them.